Hi, my name is Phil Bagg, and in this video we're going to explore algorithms in Key Stage 1. I believe that once you understand the concepts behind algorithms, then you'll be better equipped to teach it and on the lookout for better ways to express this concept in your own classroom. Here we have a semantic wave. These are great for thinking about curriculum sequencing. The idea is to take a complex idea such as an algorithm and unpack the concept until we get to the most concrete examples and simplest meanings. Starting at the red arrow, you can see us doing this on the downward curve from left to right, unpicking sequence and precision. At the bottom we have the most concrete everyday examples of an algorithm, such as class tidy-up routines or brushing your teeth. Then the curve to the right is where we repack meaning so we can get back to the fullest meaning. Some of these are characterized by some, so they don't apply to every algorithm. We're building back complexity, getting back to the full meaning. In the next slide we're going to unpick this even more. Algorithms need a sequence, one step after another step. Algorithms are ordered. Here is an example of a tidy up algorithm. Tidy, chairs, coats, line. If children in your class are used to this routine, they will probably follow it well. But a new class or a new child might struggle. It is far too ambiguous to be a good algorithm. You as the teacher could demonstrate the ambiguity in this by misinterpreting some of these instructions. You could lay chairs on their side, stack coats, draw a line on the board. Maybe the children could come up with their own alternative approaches to this imprecise algorithm. So algorithms tell you exactly what to do. They are precise and unambiguous. A more precise, detailed instruction is harder to misinterpret. Around you tells us where to tidy. 6 only tells us how high to stack the chairs. By the door tells us where to line up. Detail makes our algorithm more precise. Algorithms are used to plan all types of sequences. Sequences which will never become code, such as lining up in the morning or using the lunch hall at the dinner hall at lunchtime. Algorithms are also used to plan code. Our tidy up routine is an example of an algorithm that will never be converted into code. Algorithms can be used to plan bebot routes using symbols or words. Here we have a bebot route planned using cards. This algorithm plan can be turned into code to run under a digital device. This card-based algorithm can be followed step by step and the instructions punched into a bebot. Algorithms are written for another human to understand. Code is written for a digital device to follow. Algorithms can be used to plan Scratch Junior programs using symbols or words. An algorithm plan can be turned into code to run on a digital device. A sketch can be used to plan a Scratch Junior program using symbols or words. The plan can be turned into code to run on a digital device. At this stage it is great as a plan, only will improve the final programming project. It has lots of details, so we might say it is developing precision. However, is there a clear order to it? Asking pupils to number the actions will help to make it sequential, give it an order and turning it into an algorithm. Completeness is important when writing instructions in advance. You can demonstrate this by asking pupils to spot the missing instruction in any algorithm. What would happen if this was missed out? Well, in this case, you'd leave your coats at school, and the next morning you wouldn't be able to wear them to school. So algorithms need to include all the steps. Here we have 2 written algorithms. Will these algorithms produce the same outcome? You could split the class into 2 groups and get them to follow one of the algorithms and see if everyone gets tidied up and ready to go. There are minor differences, but essentially both algorithms do the same thing, so the outcome should be the same. Algorithms can be written in different ways and still do the same thing. Here we have 2 algorithms written in a different order. will these algorithms produce the same outcome? You could split the class into two groups and get them to follow one of these algorithms, see if everyone gets tidied up and ready to go. Unless there is some problem with where you stack chairs affecting how you tidy, both these algorithms are written in a different order but still do the same thing, still have the same outcome. In the last slide we demonstrated that some algorithms can be written in a different order but still do the same thing. Here the two algorithms are organized in a different order again. Can you see any problem with this? Yes, you spotted it. Lining up is an end task that stops other tasks being carried out. Or if you stop lining up to carry out other steps on the algorithm, you may not be ready to go at the end. This means that if you change the order of some algorithms, it can change what they do. One of the main reasons teachers think code is the same as an algorithm is that often the algorithms that people come up with are the same or almost the same as the code instructions. Look at the Scratch Junior code block. It is almost the same as the drawn arrow in the algorithm. Originally everybody understood that an algorithm was written differently because it was much easier to understand than the complex text code. However, the blocks and buttons on our simple digital devices that we're using in Key Stage 1 are almost exactly the same. Technically, if a set of instructions are exactly the same as code, they are code. However, or we're planning in code. However, as pupils are planning, we can still call this an algorithm for younger pupils. But as teachers, let us not fall into the trap of believing that code and algorithms are the same. There is overlap, but there are crucial differences as well. Finally, you may have seen many examples of an algorithm. An algorithm can be written in any ways as long as it is clear, precise, ordered, and can be understood by another human. Here is an algorithmic knowledge summary. There are many great resources available that tap into lots of these elements. And maybe you'll be someone who develops some things just for your class as well. Now you've seen some of the things that you want to develop. My thanks to the Everyday Computing team who have published a great sequence trajectory that I have drawn on quite extensively for this video. Do go and look at their research. My thanks also to Jane Waite for taking the time to explain why algorithms written in code are not really algorithms but really planning in code. As always, all errors are my own. If you want curricular computing support, then please get in touch. I work inside and outside of Hampshire, face-to-face or online. In Highest Hampshire, inspectors provide resources on every area of the curriculum. To be fair, there's much more literacy and maths and science resources than there are computing on our Moodle. You're welcome to subscribe if you are in or outside of Hampshire. We welcome everybody. Thank you very much for listening.